Okay, so for today, think about, in math, oftentimes what we want to do is we want to use math to model stuff in the real world. Like my background's in physics, I think I've mentioned that before. What physics is almost exclusively about is just finding ways to build math models to understand the way the universe works, to make accurate predictions. Thank you. Here, I'm going to give you a handout. Here you go, Melanie. I'll give you one of those. Yeah, that's the one. It's about using math to make predictions about the universe, and that we do that at there's different branches of physics, use different types of math models. But like when you guys, how many people are in physics, or nobody's in physics yet, right? You guys will take that next year or the following year. You'll do some things like you'll make some predictions, I would assume. Well, if you were going to shoot a cannonball up in the air and you know what the initial velocity is when it leaves the tube and you're on a flat ground, you could make a prediction where that's going to land. And it's a pretty accurate prediction, okay, using some math. Not real complicated math. Sometimes, usually when we're doing things like this, there's going to be a single function that's going to help us make that prediction. Like in the case I just described, it would be a quadratic function, where the distance is going to be a function of the time it's in the air, and you'll see that stuff in a year or two. And we'll look at some of that stuff actually. We'll probably look at an example very similar to that, and within about a month and a half, something like that maybe. Sometimes though we have to do some weird things. Let's think of another example we might want to model mathematically. We might want to use some physics, but this is going to be a little different than what we've maybe talked about in the past. So imagine now that you're going to go really high up in, like a hot air balloon. You're going to go way up there, way up high. And at some point the balloon's it's going to reach its maximum altitude, and you're going to hover there, and you're going to jump out and parachute. Okay, so I want you to think about what would that experience be like now. So think about about what that's going to be like. You're going to fall. Imagine just in your mind, think about this. Your stomach's going to fall, and you get that weird sinking feeling as you accelerate towards the ground when you first jump out. What's going on there? Say it again. Awesome. Okay. Yeah. So if we were looking at, for example, your speed as a function of time, right? When you first jump out of that, when you first step out of the parachute, out of the hot air balloon, your speed is 0, right? But for a period of time, what's going to happen to your speed? Oh, you're going to accelerate, and you're going to uniformly pick up speed, right? Okay. Will you accelerate forever? What happens eventually? Say it again. I think. Okay, but even before we deploy our parachute, something else might happen here. Are you going to accelerate forever? So let me ask you this: if you were to drop a penny off the Empire State Building, would it kill somebody if it hit them? No, it wouldn't. It wouldn't. I know I've heard that one, but it wouldn't. How come? No, that's not it. Because if we did this experiment, if we went to a planet without an atmosphere, we were walking around in spacesuits at the bottom of a building like the Empire State Building, and somebody dropped a penny off of that building, it would kill you. It would kill you deader than dead. It'd go right through your helmet, and it'd kill you. But not on Earth. How come? What on Earth is different? No, gravity would be the same, let's say. Planet just like Earth. But there's a reason that if I drop something like a pebble or something from the top of the Empire State Building, it will not kill you. If you do the math, if you calculate how fast it would be going if we were living in a vacuum, it would for sure. But what's the difference? Yeah, there's air resistance, isn't there, right? So at some point, and it's there. We don't really, if you wave your hand around, you don't really feel the air, but sometime when you're driving down the highway in your car, stick your hand out the window, and you can pretty easily convince yourself that it's there, right? You feel the resistance. So yeah, at some point, the wind resistance is going to match the weight of the pebble or the penny or whatever it is, and it's not going to accelerate anymore, right? And what do we call that speed that it hits? Anybody know? Okay, close. Terminal velocity, right? When something falls as fast as it's going to fall because it's falling through air or through a gas or through a fluid or whatever it is, and the friction is going to push up hard enough that it won't accelerate anymore. For a person, you can vary your terminal velocity depending on how, like if you're laying flat as you're falling, you're going to fall a lot slower than if you dive, right? I mean, but for a person, it's probably something like 120 to 150 miles an hour, something like that. It's probably your terminal velocity. So at some point then, we've already got 2 chapters in our story, right? You step out of the hot air balloon. For a period of time, your speed increases, right? Okay, there's chapter 1. Chapter 2, you hit terminal velocity and your speed doesn't increase. You just fall at that same speed, at, as long as you want to, I guess. At some point, though, we probably better deploy our parachute, right? So what's that? Anybody ever parachuted? No, I haven't either. But we can imagine probably what that would be like, right? So if you pull the parachute, what are you going to experience? Just imagine that you're in that harness. I mean, it's going to be a pretty dramatic thing. What are you probably going to experience if you pull that parachute? It's going to feel, you're going to get jerked pretty hard upward, aren't you? There's going to be a strong force on you that's going to slow you down. It's going to decelerate you, agreed? Right? Because it's going to catch the air and it's going to slow you down over a period of a few seconds. And so your speed is going to decrease again quite a bit, right? For that period where the parachute's deployed and it's catching the air and it's braking you as you're moving down. But it doesn't stop you, of course, right? Eventually, you just float down at a much, much slower terminal velocity because now there's a lot more air resistance with that big parachute hanging above you, right? And then finally, you hit the ground, and that's a pretty large force. I mean, not huge. People they don't break legs too often when they're parachuting. You hit the ground and you go to 0. So really, there's 5 chapters there. You accelerate out of the hot air balloon, you hit terminal velocity, you decelerate massively when you pull the ripcord, you float down at a slower terminal velocity, and you stop over a period of a second or half a second when you hit the ground, right? Okay, that's a lot to ask for a math function to model all that stuff, don't you think? Right? I mean, there's no way you're going to find a single function that's going to do all those things at the same time unless you're able to break different functions up into pieces and stitch them together, right? Which is kind of what we're going to look at today. It's called a piecewise function. Here's what a piecewise function looks like. Here's an example. Okay, so here's a piecewise function that has 3 pieces. First of all, notice what a piecewise function looks like. It's got our normal function notation. It's equal to, and then we've got this script bracket up there. The script bracket with 3 rows next to it. That's the way we write a piecewise function. Whenever you see something like this, you know that there's probably going to be some pieces to that piecewise function that are coming. Okay? In this case, there are 3. Each of these pieces has 2 parts. It has the function part. That tells us what the function looks like, right? That's the rule that we use to graph the function. And it has a domain. It tells us where that particular function lives in the xy plane. For what values of x is this the function that we're using? Well, in this case, whenever x is less than or equal to 2, our function is defined as the red piece, we'll call it, 2x. Okay? For the values of x that are greater than -2 and less than +4, it switches gears, and the function becomes something different. It becomes -1 minus x. So it changes rules completely. Okay? And then we'll call that the blue piece. When x is greater than or equal to 4, it shifts gears again, and the function has a constant value of -3. Okay? So what we're doing is we're dividing up the domain of all real numbers into these 3 little pieces, these 3 little intervals, right? Each interval is associated with one of the 3 pieces of this function. Okay? Give me, just quickly, just give me like a 1 to 5 on, you getting the idea of what this kind of is? I mean, we'll graph these things and look at them in much more detail. But where are we right now on this? Okay, that's good. We got ways to go. I understand that. So the first thing we probably want to do here is maybe let's see something. I think I forgot a piece. I want to try evaluating. a function. And I don't know why that part didn't get on there, but look at your notes. And let's just take a quick look at, how about number 1? I'm going to add a page in here. Okay, so here's our piecewise function. So I'm not going to use the word if. Usually with piecewise functions, we don't write the word if, we just put a comma there that's separating the rule, you know, kind of the equation or the rule from the domain where that part of the piecewise function is defined. Okay, how about this then? Can somebody tell me what is f of negative 5? How would I know? Anyone want to take a stab at how I might evaluate that function? If I'm inputting x equals negative 5. Okay, so negative 5, first of all, we have to ask ourselves which piece of the function are we working with here, right? It's the red piece, isn't it? Because negative 5 fits in this part of the domain, right? So f of negative 5 is going to equal, well, I'm going to, remember, whenever I'm evaluating a function, I just open up an empty quantity to dump the contents into, right? So I end up with my x value squared minus 1. My x value is negative 5, so I get, what, 25 minus 1? Everybody agree? 24? Okay. So 1 point on the graph, and this would be on the red part of the graph, is going to have coordinates negative 5, positive 24. Okay? How about f of negative 2? What do you think here? Cray, which part is negative 2 going to be a part of? Which piece of the function, the red or the blue? The blue, yeah, right? Because the blue includes negative 2, right? So f of negative 2 is equal to 5 times negative 2 plus 3, so what, negative 7? Is that right? So we get the point negative 2, negative 7, etc. That's probably all we need to do, right? You get the idea, okay? All right, so now let's look at how we might graph these things. So when I graph this, there are going to be 3 distinct different parts of this graph. There's going to be the part of the graph where x is less than or equal to negative 2. There's going to be the part between negative 2 and positive 4, and there's going to be the part where the x values are greater than or equal to 4. So the boundary, would everybody agree here that the boundaries between the pieces, the boundary between red and blue, would be the x value negative 2? Okay, give me thumbs on that. Right? Okay. So then, if I graph the equation x equals negative 2, that's just a vertical line, isn't it? Right? So that vertical line is going to act like a boundary in the xy plane that's going to separate the red part from the blue part of that function. And by the same token, 4 is going to be the boundary between blue and green. Okay? So I could think about the red region as being that entire part of the xy plane that's to the left of the line x equals negative 2. Okay? So when I graph the red piece of the function, it's only going to get graphed in this one region. Everybody see that? If I graph the line y equals 2x, the line y equals 2x is just a line, would everybody agree, with a slope of 2 and a y-intercept of 0? Right? So it just goes through, it's just a line that goes through the origin. I didn't draw that very well with a slope of 2, right? But I only get to draw that or graph that piece in its own domain, so I only get to draw that where the values of x are less than or equal to -2. So that's a graph of the equation, y equals 2x. But on my piecewise function, I would have to go back and erase this whole part up here because it doesn't exist there. It only exists in that part of the domain where x is less than or equal to -2. Okay, give me thumbs. Okay, can anybody ask a question? If you're not feeling great about that, try to ask a question. It's good practice too. Anybody got a question they could ask me about that? For clarification? Like, okay, Mr. Ray, I don't get this part. Yes, sir. Mm-hmm. That's where I would start it, exactly, right? This function is only defined, y equals 2x is only defined, and therefore we can only graph it for the x values that define that piece, right? When we say that it's only defined in math, what we mean by defined is it only exists for those x values, right? Okay, so how do we graph that then? It gives us a practical problem that we've got to deal with when we're trying to graph these things. One approach would be what I just did, which would be to just graph the function y equals 2x. Maybe you could maybe do it lightly on a piece of graph paper or something. Now we're going to come up with a better one in a second, but I just want you to see that this would work. I could like lightly trace that line and then go in and more heavily graph the part that's in the red region that exists for the x values less than or equal to -2. Everybody see that? That's one way I could do this, okay? Because I only get to keep the graph for the values of x that are to the left of x equals -2, well, but including -2. So I really, what kind of endpoint should I have on this ray that I'm drawing that corresponds to the red piece? It's including the red piece up here, notice. The red interval has an equal sign on the inequality, so it's including the value of -2. Is this going to get an open or a closed endpoint then? It's going to be closed, isn't it? Good. Okay, so that's what that piece looks like. Okay, that's pretty inconvenient though, to have to graph the whole thing and then go back and erase it, right? What could we do instead? Well, how many points are required to draw a line or something that's linear like a line segment or a ray? 2, right? I only need 2. So I could always go back up here and I could use a t-table. This is a great little strategy. I could go up here and use a t-table and just come up with 2 ordered pairs that are in the red region of the xy plane, in the domain of the red piece. But let's pick convenient ones. One of them we probably want to pick is the endpoint, right? Because we want to know where this thing stops accurately. So we'd pick the value x equals -2. Well, if x equals -2, y would just equal 2 times -2, right? -4. And so I've got one point here with coordinates. That's just an ordered pair, isn't it? I've got one point with coordinates -2, -4 right there. And I just need one other one. Well, I don't know, let's pick, doesn't really matter. Let's pick -4, I guess. So if I pick x equals -4, then y would just equal, you know, I can write it this way. F of -4 just equals 2 times -4 equals -8, right? So I get another point at -4, -8, which is right there. And then all I have to do is just start at this endpoint, connect and extend, and it goes forever. Okay? All right, give me a 1 to 5 again here. I'm just trying to see how we're doing, okay? Be honest with me. I want to know if I'm making progress on this, okay? Okay, can anybody ask a question? Be brave. Anybody that's not feeling super about this, what's a part that's not super clear? Yes, ma'am. Oh, why do I shade? Okay, good question. The shading, that's not part of it. That's just there for convenience. I only put that there. Thank you for asking. I'm glad, because that probably was maybe that's, people were wondering, is the shaded region necessary? No, not at all. I just put it there just to kind of illustrate what part of the XY plane corresponds to the red piece. Okay, wouldn't have to be there. Shouldn't be there, really. Just there to help you see, okay? Any other questions on that? Yes? You think you got it? Okay. Anybody else? Nope. Okay, all right. How about the next piece then? Okay, so where's the next piece going to live? The blue piece is going to live between the x values of -2 and 4. So what's the blue region going to look like? And again, the blue region, that's just for us, to help us visualize where we're going to graph this. What's that going to look like? Yeah, between those two boundary lines, right? We know that somewhere in this region of the XY plane in there is the blue region, right? That's going to correspond to this piece, because we can only graph it between the values of x equals 2 and x equals 4. And again, we just need to know what that line looks like, so we'll just make a little t-table and pick two useful points. What would probably be the best points to pick? Any 2 points is going to define that little line segment that we're going to get, right? But which 2 would be the most useful? Ah, yeah, we'll use the endpoints. Even though, look, even though those points are not included in the blue region, they're going to be the endpoints, aren't they? It'd be nice to know where the endpoints are. So if we plug those values in, if I plug in -2 into the blue function, I'm going to get, for the blue line, whoops, I would get, if x equals -2, y would equal -1 minus -2, which is just 1, isn't it? Right? So I get that ordered pair. But we don't really get to include -2 in the blue region, so what kind of endpoint am I going to put there? Open, right? Because it's not actually included, it's just an endpoint. Okay, so I'll grab one of these guys, and -2, 1, so it goes right there. Okay? If I plug in 4, -1 minus 4 is -5, so I get another endpoint here at 4, -5. So let's grab that one. Over 4, down 5, so it goes right there. And now all I have to do in between is just connect those guys. Okay, give me 1 to 5 now. How are we doing? Okay, all right, I feel like this is getting better, okay? And then for the green region, that's just going to be everything to the right of the line, of the boundary line x equals 4, right? Question? Oh, yeah, whoops, I'm sorry. Yep. There we go. Okay. How about the green question? Oh, you did? Okay. All right. Okay. That's good. I like it. So there's the green region. Green region, that's a pretty easy one to graph. I don't really, I mean, the line y equals -3 is just a straight horizontal line, right, at -3. I don't really need points. If I want points, I can pick a couple points, but we don't really need them. And what kind of endpoint do I get for this green piece? Yeah, I'm going to get solid, aren't I? Good, because I'm including the equal sign, I would do that. And there's my beautiful picture, okay? All right, so now based on that picture, next issue is, let's look at this piecewise function, and let's see if we can determine, I can't remember if no, I didn't, darn it. Okay, so we're going to have to kind of look at all three of these pieces taken together in this piecewise function, and all together, what's the domain of the function? Think what it means to ask what the domain is. That's the set of all the possible input x values in this case, right? Inputs are x's. Another way of saying it is, what are all the possible x values that an ant could step on this function? Yeah, there's nothing missing, is there, right? The ant would, I mean, he'd be kind of a weird journey, but as he walked along the red function to the right, he's going to kind of beam up to the blue function, and then walk down that ramp, and then he's going to beam up to the green function when he steps on 4. Does that make sense? But there's never a place that he can't step, okay? So the domain is all rails. So what about the range? Okay, is the 1 going to be included or not? You're right, it's not included. Good. Right, so very good. So in this case we get negative infinity up to 1, and we'll have to leave that as an open-end point at 1. And how else could we visualize that? If I took all of these three parts and I projected them onto the y-axis, there'd be some overlap, but that's okay, right? The red piece right here, if I projected it onto the y-axis, would just look like that. Agreed? The green part of the function projected onto the y-axis looks like a single value. It's only got one y value, which is 3. And the blue one is going to go from there all the way up to there with an open endpoint. Well, look at that. That orange interval includes everything from positive 1 down to negative infinity, but we don't get to keep the positive 1. Okay? Give me 1 to 5 on that one. Okay. Oh man, that's great. That's a tough one usually. Okay? Okay? Let's try another one. How many pieces obviously here? 3. Okay. Where are the boundaries between the pieces? What x values? Okay, 0 and 6. Good. So I could maybe, if I wanted, you don't have to use the colors on this. I mean, you won't be able to. You don't have a fancy board like this. But if we want to take advantage of those colors, there are the 3 intervals, right? If we color code this thing. Okay, so no big deal really. Like, what would I pick for my, what's one, if I want to graph the portion of this piecewise function that's in the red region, that's a line, isn't it? I guess I should maybe mention that. If we go back to this last example, it was easy to do. One thing that made it very easy to do was the fact that all 3 parts of this were lines, right? If I look at those 3, if I write down those 3 equations, the red piece just looks like the line. I'll write it up here. Y equals 2x, right? Everybody agree? The blue piece looks like the line. If I put it in slope-intercept form, wouldn't the blue piece just be the line y equals negative x minus 1? Easy to graph. And the red piece looks like a very simple line, or sorry, the green piece looks like a very simple line, y equals negative 3. All very simple to graph. That made it much, much easier, didn't it? It'd be a little tougher if we had some other weird functions that we had to graph that weren't linear, okay? For now, we won't be dealing with that. So same thing here then. We're fortunate because we've got 3 lines, so it's easy to graph. The red one is the line y equals negative 3x. The blue one is the line y equals 1/2, negative 1/2 x minus 1. And the green one is just the line y equals x minus 7. Okay? So if I'm going to pick 2 points in the red region to define that line, what should one of them definitely be? What x value? 0, for sure. Right? So we're going to use if I plug 0 into this function up here, this line, I get 0 for y. Right? And then another one could be anything that's convenient. So how about those two? Open or closed endpoint on the red one? Open. Yeah, there's no equal sign, right? So the red domain does not include 0. That's just the boundary, the right endpoint of that piece of the piecewise function. Okay, so we've got these ordered pairs. Got an open endpoint at 0, 0, and I've got a closed point, not an endpoint, at -2, +6, and then I would just connect those. I'm going to cheat here and make a really straight line so this looks better. There, that's a little better, right? So there's the red piece, okay? How about the blue piece? What x value should I definitely pick for the blue piece? Everybody, what should I pick? 0 and 6, yeah. So I know where it ends at the boundaries, right? Okay. So if I plug in 0, I get -1. That makes sense. If I plug in 6, -1/2 times 6 is -3 minus 1 is -4. Open or closed endpoints? Both. Yeah. Closed on the left, open on the right. So 0, -1, I've got a closed endpoint there. I've got an open endpoint at 6, -4. And I'll just connect those endpoints. There we go. And then for green, what's one endpoint I definitely want to use? 6. For sure I want to use 6. And then whatever else is convenient. So at x equals 6, do we get an open or closed endpoint? Open. Yeah, it's open. So 6, -1 is right there, and 8, 1 is right there. And there's my third piece. Okay, give me 1 to 5. How are we doing on that? Okay. Okay. All right, so now, what about the domain this time? Be careful with this one. Are there any missing x values? Anybody see a missing x value? Melanie, you see one? You see an x value that got skipped over? Ashley, think you got one? 0. Okay, is 0 skipped over? Okay, 6 would be the one that skipped over, right? 0 is okay, because even though there's an open endpoint at the right endpoint of the red piece, there's a closed endpoint that kind of fills in that gap in the domain, right, for the blue piece. But look what happens at the transition between blue and green. Neither one of them gets to claim that endpoint, right? It's not a part of either the blue domain or the green domain. And so the domain of the entire piecewise function then is everything except 6, right? Two ways we could write that. We could write that as x we could write that as x is not equal to 6. X is not equal to 6, or if I want to write that using interval notation, I'd have to do something like this. I'd have to say -infinity up to 6, or, and a lot of times we just use a comma for an or, we've seen that before, or 6, or x is greater than 6. Okay? We could also use an or symbol there instead of a comma, either or, depends on which textbook you're using, okay? What about the range? If I were to project this whole thing onto the y-axis, where does the range start and where does it end? Say it again. Okay, -4. It looks like the bottommost y value, right? The ant could never go any lower than -4. Could the ant even go to -4? Okay, good. So we're going to put open parentheses, right? Parentheses for an open endpoint at -4. And then the ant always has a y value to step on from that point up, doesn't he? Right? These pieces all overlap enough that there are no gaps in the range from -4 on up to infinity. Okay? You're probably getting tired of this, but give me a 1 to 5 again on this. Okay? Okay? All right. Okay, so now let's go in reverse. Can you give me the rule, right? You know, they are just saying it. No. Can you give me the rule that goes with this piecewise function? So we want to work backwards. Now we're given the graph, and we want to see if we can write the piecewise function. When it asks for a rule, it's asking for kind of the formula or the equation, right? Maybe it helps to break this into pieces. So we got a blue piece down here. Let's make this the red piece. Okay? So we know we can write the template. How many pieces in our template? 2. Okay. What about let's do the red one first. That's easy. Actually, let's not. Let's do the blue one. So we'll go from lower, just like the other ones did. We'll be consistent. We'll go from small x values to big x values. So the blue piece is defined for what domain, first of all? What values of x? All values of x less than or equal to 0, right? Because that's a solid endpoint. So it's keeping an ant stepping on any x value from -infinity up to and including 0 would be walking on the blue piece of the function, right? So the blue domain, oops, got it backwards, less than or equal to 0. When x is less than or equal to 0, we get this function. That's a line. Let's see if we can just come right up with the answer. What's the y-intercept of this blue line? 0. What's the slope? So 1. So I just get x. Y equals 1x plus 0. So I just get the line y equals x, right? Everybody agree? But I don't need to put the y there, do I? Because I've already got my y right here. I'm just putting what is the y equal to for the blue part, and it's equal to x. Okay? How about the red piece? What's the domain of the red piece? For what values of x would an ant be stepping on the red piece? Greater, everybody see greater than 0, but not including 0, because 0 is included in the blue piece. You have an open endpoint there. So the domain when x is greater than 0, that's a pretty easy equation. Y is equal to what there? 2. Okay? Hands are getting tired, but flash me a 1 to 5 here again. Okay? All right, so before we jump into this stuff, I want to show you how to do this on a graphing calculator and on Desmos. So I'm going to skip ahead a little bit. Piecewise functions. So here's how we would do this in Desmos. How much time do we have? Oh boy, okay. We'll deal with it tomorrow. Is that enough math for one day? Okay.